Hello guys, welcome back to Maison African Motives, still on Mechanotechnics and working on metal cutting machines. This is a similar question that you're going to work with from March 2018 question paper related to the March 2023 exam. So I want you guys to understand they are actually repeating a lot of things in our exams. So let's consider working more question papers. The more we do more question papers, the more we know the mind of our department. How do they want you to answer and attempt these questions? Okay, so without wasting much time, let me quickly rush through the question. We are given Fig 1 shows the setup of a cutting tool held in the tool holder of a shaping machine. The ram of the shaping machine has a mass of 100 kgs and is in operation with a cutting stroke length of 250 millimeters. The total work done during one cutting stroke is equal to 125 joules, and the coefficient of friction between the ram and the slides is 0.2, just similar to the one that we had for March 2023 exams. So here we are given the clamping screw, that is the clamping force of 1000 Newton, the cutting force at the end, and also the distances from A to this point at 1000 and also at B. And we've got our question. The first part of the question, calculate the work done to overcome that is on 3.1 to overcome the friction between the ram and the slides. 3 marks for that. Okay, so if you watch the March 2023 paper video that I had, then I'm not going to waste much of my time here. I'm just going to explain so that we just understand more, just to remind you guys. Okay, so here we need the work done to overcome friction, which is I'm going to write this way. Okay, the work done to overcome friction. So that's 3.1. So the work done to overcome friction, I'm going to have it this way. So remember that in our formulas or our calculation, that work done is simply the force times the distance. So the force that we are going to talk about is the frictional force due to friction. And the length or the distance is the stroke length, which is our L. So this is the formula that we are going to have the work done to overcome the friction. So do we have the frictional force? Do you have the length, the stroke length? Okay, let's see from the information that we were given before. If we are to check here, we have got the mass. Let's just take our information. We've got the mass of 100 kgs and the cutting stroke length of 250 millimeters. So we've got the mass there and the stroke length. All right, so let me just have my information. So we've got a mass of 100 kgs. The stroke length at that moment is 250 millimeters, which you can convert to meters, divide by 1000, 0.25 meters in this case. And also we are given the total work done on one cutting. Take note, this is on one cutting stroke, which is 125 joules and also 0.2 as our coefficient of friction. So we've got the total work done and the coefficient of friction in this case. All right, so the total work done, I'm going to write this way, 125 joules. That is for one cutting stroke, and also the coefficient of friction of 0.2. Take note, at that moment, G is going to be at 9.81 meters per square second. Okay, so with this information, how can we obtain, because we do not have this friction, how can we obtain the frictional force? We have got the stroke length, this part. So remember that if we are to consider from our coefficient of friction, the one that we are given here, we have got a nice formula that we have got, that the coefficient of friction is simply the horizontal force, which is the frictional force over the normal reaction. So we've got the frictional force over the normal reaction, which we can simply make the subject, in this case, the frictional force, because it's the one that we need on our formula, this frictional force. So this is same as over 1. So you can just simply cross multiply so that you can have the frictional force. 1 times the frictional force, that is the frictional force, is equal to the coefficient of friction times the normal reaction, which I said it is just equivalent to the mass times the gravitational acceleration for the given, since it opposes for this given information. So we are going to have the coefficient of friction times the mass times the gravitational acceleration, representing the normal reaction, which is opposing to the force. Okay, that is our normal reaction. Okay, so that means we can substitute everything. The coefficient of friction, we have got our coefficient of friction here. That's 0.2 times the mass. At that moment, it is given as 100 times the gravitational acceleration of 9.81. So this gives us the frictional force. So the frictional force in this case is going to be 196.2 in Newton. Okay, so we can take now our frictional force. All right, so we've got our frictional force here. So we can substitute back into the formula. The frictional force that we obtained, take note, 192.6. So we're going to have this so that we can obtain our final answer. So the work done to overcome the friction is going to be the frictional force of 196.2. So that's 196.2 times the L, which is represent the distance. That will be our stroke length in meters, 0.25. So we have got the work done to overcome the friction in this case, which is 49.05 measured in joules. So take note, work done is measured in joules in this case. Okay, so the purpose, someone might wonder, why are we multiplying by the stroke length? Remember, we are given the work done per one cutting stroke. So that is why we are using the stroke length. Okay, that is the distance that you're supposed to use the stroke length. Okay, let's see the other part of the question. We are also given on the other part of the question, which is on 3.2, now to calculate the cutting force exerted on the cutting tool. On the cutting tool, this is our cutting tool here. If we check properly on our diagram, we've got our cutting tool here, which is a cutting force that is presented at the end or at this part here. So this you can write as F1, or you can write just FC. So here I'm going to use it as FC to represent the cutting force, okay? Or you can write as F cutting in full like this, okay? So it's up to you guys the way that you're going to write there. Okay, so how can we have, or how can we obtain that force at that point? Okay, this is what we have according to our information. 3.2, so we need to calculate the cutting force, the one that I wrote as FC. How can we obtain this? Remember, from our work done is simply force times distance. This is the normal formula that we are supposed to have. Work done is simply force times distance. So if we are to consider F, which is the force, we can make this the subject by dividing by L both sides by L both sides, so this can cancel. F is simply equivalent to the work done over the length, which is the distance, which is the force. So meaning to say F can be calculated from this formula. So meaning if we are to calculate the cutting force, it is going to be FC. This is going to be the cutting work done, which is the WC, which is going to be WDC like this, representing the cutting work done. Since we are calculating the cutting force, we must have the cutting work done over the stroke length L. We have got the stroke length, but we do not have the cutting work done. Where are we going to have this from? Okay, remember guys, what I told you, that this is simply a sum of from the total of work done that we have got here. If you consider what we have on this part, we have got the sum, the total work done of 125 joules, which is simply the sum of the two. So the total work done is simply the sum of the frictional work done that we've got, which is the work done to overcome friction, and the cutting work done, which is in this case, is the one that we are supposed to calculate here, so that we can calculate the cutting force. So we are supposed to add the cutting work done. So these are the only work done that we have. The total work done, which is equal to the frictional work done, the one that we got from the work done against friction. We calculated this before here. And the one for the cutting work done, the one that we are supposed to calculate for us to obtain FC. So this is what you can have, and we can just substitute our values from here. We have got this total work done as 125. So 125 is equal to the work done, which is to overcome friction, which was 49,05. So this is 49,05 plus the cutting work done. All right, so you can even write in full cutting work done, or okay, and any way that you understand, guys. So transpose the 49,05 to the left-hand side so that we can subtract. This is going to be 125 minus 49,05, which is going to give us the cutting work done. And our cutting work done is going to be 75,95, which is measured in joules also. So with this formula that we have formulated from work done and made the force the subject, we are going to have our cutting force as the cutting work done of 75,95 joules divided to the length, which is the stroke length, our distance that was moved, that is 0,25 meters. So we are going to divide with that length, okay, which is our stroke length, 0,25 in meters. So this is going to give us the force. And remember, your force is measured in newtons. So that's 303,8 newtons. All right, so that is our cutting force in this case, meaning to say on our diagram here, if you are to consider properly, we have calculated this force at this point. This is the one that we calculated, which is 303,8 in newtons. All right, then the last part of the question, they are saying we are supposed to calculate the forces exerted at the two contact points A and B. If the clamping force is in the clamping screw is 1,000, which is this clamping screw, that if there's a force of 1,000, which is our clamping force, what is going to be the force at point A and also at point B according to our diagram here? So this type of equation, I said, guys, according to your moments, you can answer this to find the force at A and at B. Because here, this is simply a point, you are simply having a reaction at B, this one. It's a force that you're going to have. There's a distance between this point and this point. Also, the same thing at A here, we've got a force that is going to be affected at A. And also minding that there is 1,000, which is on the screw, the clamping screw, that is going to affect on our cutting tool. So this is our cutting tool. So if you are to check these forces, the cutting force at the end here, and these three forces, they are the ones that are acting on our cutting tool, only these forces. So we can present this from our moments concept, okay? So let me just write it aside here. So this is 3.3. All right, so we can use the moments concepts to solve this, okay? So having our cutting tool, I'm just going to have this cutting tool in a horizontal way. So I'm just going to take this in a horizontal way like this, okay? So if you check, we had the cutting force at the end. This is the first force that we are having. So I'm going to have it here at the end. So this is your cutting force presented as a point load of 303,8 newtons, okay? From this force that we have in between, from this force to the point A, there's a distance of 50 millimeters. So in between A is going to act as a reaction, a support at A. So this is our point A. So between this force and A, this is between this point and A, there's a distance there, 50 millimeters. So here we've got a distance in between these 2 points of 50 millimeters. All right. The same thing, if you move from A to this point of 1,000 Newton at the clamping force at our clamping screw, there is a distance between this to this point here, or to this force that is acting, of 40 millimeters. So we are going to have a distance. We have a distance between here of 40 millimeters. To the force, that is our clamping force of 1000, which is in between. So we are going to have a force in between here. So we're going to have 1000 Newton. So that is where we have our 1000 Newton, which is acting at this point. Okay. From the 1000, we move a certain distance again to reach the point B. So these are distances. So to point B, there's a distance 40 millimeters to reach the point B. So we are going to have 40 millimeters. Then we reach the point B. All right. So this is like this, 40 millimeters. Then we are having point B at the end, which is a support like this. And this remaining part, we do not have any other force that is going to act there. So with the law of moments, guys, we can use them to calculate the forces that are acting at A and the ones that are acting at B. Remembering that the sum of the clockwise is equal to the sum of the anti-clockwise moments, or the sum of the anti-clockwise is equal to the sum of the clockwise moments. So let's start with A. So let's start by taking moments about A. So taking moments about A, taking moments about A. Okay, so if you have to consider A, B, as it moves to A, B is moving this direction, which is anti-clockwise. Remember, a clock moves like this, that's clockwise, and anti-clockwise is opposite like this. So this is anti-clockwise, okay? So B moves in the anti-clockwise, so I'm going to use the formula. The sum of the anti-clockwise moments is equal to the sum of the clockwise moments. So B, as it moves to A, it's anti-clockwise. Remember, it's force times distance. So it's force at B times the distance. B to A, you combine these two distances between B and A. That is where we have got 40 and 40. So if we add 40 and 40, that is 80. So it is going to be B times 80 like this, okay? Do we still have another anti-clockwise? Which part that moves back to A in this direction of anti-clockwise? If you check the FC that we had here, as it moves to A, it's moving this direction, which is anti-clockwise. So we still have another force. So we add that one plus 303 comma 8 times the distance. So 303, as it moves back to A, it moves a distance of 50 millimeters. So we are going to multiply by the distance. So that is force times the distance. Do we still have anything that is in the anti-clockwise? We do not have. These are the only forces that we had that are moving back to A in the anti-clockwise. The 1000, as it moves back to A, it is moving this way, which is clockwise. If you check, this is the direction. So that is a clockwise. So I'm going to equate on the clockwise side. So that's 1000 times the distance. 1000, as it goes back to A, it's separated between a distance of 40 millimeters. So that is going to be 1000 times 40 millimeters there. All right, so that's it. Multiply, combine everything. This is going to be 80B plus 303 times 50. That is going to be 1000. That is actually 15,190 is equal to 40,000. So on the other side, you're going to obtain 40,000. So we can transpose the 15,190 on the other side so that it can be a negative since it was a positive here. So if you subtract 15,190 on the right-hand side, we are going to obtain 24,810. Divide by 80 both sides so that we can have the force that is acting at B, which is going to give us 310,125 Newton. So this is what you're going to have in this case, all right? So with the same idea or knowledge that we are having now, we can even calculate the one that is at A by taking moments about B. So if you are to take our moments this time about B, that means we are going to have, this is not going to be part of our diagram now. That means in this case, as A is moving back to B, it's moving this way, which is a clock wise. As you can see, it's clockwise direction that you're going to maintain like this. So that means I'm going to relate the clockwise moments this time. Yes, you can still use the same formula if you understand that way. or you can still start, since I'm about to calculate A, I can start with those with that part of A, which is the clockwise, since A is in the clockwise. So A back to B, there's a distance of 80 millimeters. Remember, force times distance. So that is A times 80 millimeters. Do we still have any other force that moves back to B in the clockwise? Let's check. 1000, as it goes back to B, is this direction, like this. So this is anti-clockwise. The 303.8, it's also anti-clockwise. So we do not have anything in the clockwise. We are just left with the anti-clockwise. That is, we equate to the anti-clockwise. What are we having on the anti-clockwise? 1000 back to B. So it's force times distance, 1000 times 40. So we're going to have 1000 times 40, our distance, plus the last part is 303.8. But take note, we are now considering, as we move back to B from this point to B, this is the whole distance that you consider. So meaning to say we add 50 plus 40 plus 40, which is going to give us something like 130. So this is going to be 130. So we've got 303.8 times 130. All right, so that's it. A times 80, that is 80A, is equal to, you combine everything on the right-hand side, that is going to give us 79,494. Divide by 80 both sides, by 80 both sides. This gives us the value of A. So if we divide by 80, our A is going to be 993, 675 Newton, like that. Okay, so this is our A. So that is how we can have our forces at A and at B according to the information, or according to our diagram. So it depends with how your diagram is given. How is this diagram? Where is the force? Where are the forces that you are given? Where are they located? That is the most important part. If you are having your forces, maybe they might give you one force. You work with the forces that you are given according to that diagram. If you check other videos that we had on the metal cutting machines, you'll see that the diagram, the way that you calculate depends with the diagram that you're given. And also you can even test your answers to see if truly these values are true. Remember, for you to test, you're going to use the concept of upward forces. These reactions A and B, if we add these two, must give us the sum of the downward forces. So we can actually test our values to see if they are actually true. So the sum of the upward forces must be equal to the sum of the downward forces. So which part is going up? It's A and B, our reactions, the one that are facing up. So if we add A, 993,675 plus at B, 310,125 must be equal to the ones that are facing down, which are the supports. This is the 303.8 and the 1000, these ones which are facing down. So we add these two together. That is 303.8 plus 1000 in this case. So if you add properly, on the left-hand side, we are going to obtain 1,303.8 Newton, which is the same thing on the right-hand side. We are going to obtain 1,303.8 Newton. So that is to tell that this is actually true. So if you are given a condition, you can actually test your values to see if you're in the right direction on your calculations. So this is very, very important to check your values. Even you are not given that option to test the values, just test and see if you are obtaining exactly what you are asked there. Okay, so this was our question, having a total of 14 marks. So this is actually a lot of marks in exam that you are not supposed to lose. So let's try to revise as much questions as we can. But for now, that's it, guys, from Maison African Motives. Till we meet again.